me and setting up always on time and so quickly. So I want to thank you for your time and hard work and putting this event together. And we all celebrate the PES. So this is one way to do it. Thank you. Thank you so much. All right. So yeah, the topic that you picked is reliability and vital signs. Can I ask why you picked this one first? Because I give you three, right? This is the one that you picked.
Yeah, we had discussions with my members from here, and they thought that this was the most relevant topic to our systems here in Kenya, because the grid system is not as developed in other countries. So we thought this will help us as engineers maybe to help in development of our.
Gotcha. Okay. So for your, let's say, the place you live right now, the house or apartment, townhome, do you have electricity all the time, like 24 hours a day?
Yeah, it's quite reliable. It's quite reliable. But not all places in Kenya have access to reliable electricity. Those near to cities and towns receive reliable electricity.
Okay. Yeah, so the topic that I have will be more like what you said, more like the cities and industrial areas that they have the lights, they have electricity all the time. For the rural areas and most of the here, at least in the United States, they have electricity as well. So what I'm going to talk about is what if we have let's say a big blackout, right? And is system reliable? Or we have the storm, like the winter cold weather, like what happened in February here in Texas. Is that reliable? And now with the renewables coming into the system, and how do we track? Is it traditional transmission or distribution grid? Is it ready to take more renewables into system? How does that impact reliability? So that's what I'm going to talk about it, okay? When I say the vital signs, I have another question. Do you like say go to your doctor's office to do the annual checkup, like on annual basis you go there and they measure your pulse rate, blood counts, and cholesterol level? Chris? Chris, do you go to your doctor's
Hello.
office each year?
I didn't get you clearly on that. Maybe you can ask again.
Okay, yeah. So what I'm is it your tradition in Kenya that you go to your doctor's office every year to check your let's say the blood and cholesterol level and your pulse rate and talk to your doctor how I mean how's your health overall? Do you go to your doctor's office each year? That's my question.
On the vital signs.
Yeah.
Okay, Johnson, maybe you can take on that. You were saying something, Jones.
People do, but we are low income economy, so it depends on the finances and the kind of cover you have. But it's recommended that we do those checkups.
Gotcha.
But,
Okay.
it varies, yes.
That helps. Yeah, I just wanted to see if I can use some of the examples I have and get to your part of your world. So the vital signs, like you said, yes. If I'm I have health insurance, right, and I can go to my doctor's office, they're gonna measure my pulse rate and blood pressure, right, and all those numbers, the indicators. That's what we call the vital signs. So this talk is about how to use these vital signs, how we use vital signs to measure the grid reliability. Especially now with all the new technologies and new devices coming into the grid, can we tell the system is still reliable with these vital signs? All right, so I'm going to go to next. The presentation I give here is just my view and does not represent the PES or any other organizations, okay? So if you ask someone on the streets, right, if they're not electrical engineers, and they will tell you keep lights on is great reliability, which is right. I mean, they probably don't want to know more, but when we have this cold weather events, when we lost power for 4 days during the coldest time of the year, and then people don't, you can tell people are, is trying to survive. And that's where they're going to say, okay, where's reliable electricity? So in February, Texas here, because this rolling blackout, because we didn't have enough electricity to power the home, and we had more than 100 deaths. So more than 100 people died because that they did not have the power in their home, because some of them, they use oxygen tank, it's powered through the electricity, and they lost the oxygen. And some of them due to the heat, the electricity heat, and they don't have the heat, and they just it was so cold, plus they have some other health conditions. Like I said, more than 100 people died because that we did not have electricity. So it could have a fatal consequences without electricity. Not just the Texas. I live in along the northeast coast of states. In 2012, we had a Superstorm Sandy. It's a hurricane. So my house did not have electricity for 7 days. Of course, we didn't have any death because it's kind of the fall, still warm weather. But we had to, the local utility had to spend $1.2 billion and try to fix the control room, try to rebuild the tower after the storm. So there's so the electricity and outages and reliability. Those are the not just the Texas, or not just it's everywhere. This is the a challenge for all of us. And here's during the storm. Here's what went on in New York City, and because New York City, most of the people they didn't have power either. So you can tell. Here's the truck with the diesel generators, and there's all the lines and come out and try to help the local community. I call this microgrid, right? And this guy in the middle and was trying to bike and charge his phone. So lots of people come to this pizza place here and they try to charge their phone. So it was a chaos. So does it mean the grid is not reliable because we lost 100 people, more than 100 people, and I didn't have power for 7 days? What does that mean? So it's very complicated. Like Chris and other gentlemen said, there's an economy reason, there's a resource. If you have lots of coal or fuel or sunshine, and the reliability might be different story. So so I add a lot of variables here. It's not the reliability. It's not like a simple numerical equation. It's a nonlinear. You have the law and courts. You have science. You have resources. You have culture. You have economy. Those are all part of the equation. And plus, the system has more than 130 years of history. The entire power grid. So it adds more complex into the reliability equation. So if we think about the electricity, right, it started about 130 years ago. Thomas Edison built his first commercial plant in New York, 1882, but he went bankrupt. He was bought by JP Morgan, essentially. because the electricity at the time was so expensive. The only rich stockbrokers in New York City could afford to use electricity. And these fellows, Westinghouse, Tesla, and Samuel Insull, they came up with a technology, use the AC system, right? You know the AC system. That's what we have today. They came up with the AC system, so they connected all the power plants, the little power plants in the city, in the industry area, in the factories. So they connected and they delivered, use a flat rate, which is you pay if you use 1 megawatt hour and you pay certain rate. Everybody pays the same. So that's how the industry survived. Not like Thomas Edison bankrupt his company. So these three guys, Westinghouse, even Thomas Edison started the whole DC, whole electricity business. But these three guys actually created the whole industry like we'll have seen today. And their goal, the time is still the cost effectiveness, low cost, so everybody can use, and reliability. You can tell reliable and safety. So those are the three goals that we inherited for last 130 years. Everyone, not just your place, Kenya, or not just here in USA, everyone, all the electricity companies, this is their goal, provide lower cost so everybody can pay their rate, compare their bill every month, and then we keep lights on. So that's the goal. Now we have very new different objective, right? Clean, we want to have no carbon emission. We also wanted to make the grid more flexible, to add the distributed energy resources like solar rooftops, connect to the grid, and batteries and EVs, electric vehicles back to the grid, all that. And those, you can tell, those are not, was part of the design, started 130 years ago. So for the last 130 years, these are the goals: cost, reliability, and safety. So the grid has become very big, and it's very hard to change to get all that. So it's all of us. It's you, especially the young generations, get into the industry and help us to make it more flexible, cleaner, sustainable, right? And also for the folks like part of your place, for the rural areas, how we can get to them without the connection. So all those are new challenges, opportunities for us to do. Like I said, the objectives have changed a lot for the last I would say 20 to 30 years, right? Instead of, we still want to do cost effective, reliability, and safety. However, we're adding more resilience, flexibility, and friendly, right? And sustainable, clean, carbon zero, all that into the grid. So like I said, you just ask a guy that's been there for 130 years and try to make a change. It's hard. So I'm gonna tell you how we can help, right? So here in the U.S., we didn't have any regulations. There's no like specific definition. What is the numerical legal definition of reliability? We didn't have that. Not until 2003, we had a huge blackout here. We lost about more than 70,000 megawatts of load. So the U.S. Congress, the government said, enough, your industry screwed up, and we want to have a mandatory standards, then you have to follow. If you don't follow, we'll penalize you. You have to pay a fine for 1 million a day per each violation. So it's a hefty fine. And that was, like I said, more than 100 years, and government decided to step in. It was all like kind of self-grown, organically grown industry here, at least. And there's no regulation. Government says you just go serve the customer, right? and then collect the bill. That's what you do. I don't want to get into your business at all. But not until, like I said, 2003, the industry just couldn't do it on their own, and they had a huge blackout. So the consumers, the public had enough. So they went to Congress. Congress had to pass the law in 2005. So what they did is that they came up with a legal definition called adequate level reliability, and they're saying the grid industry has to operate the system without instability, uncontrolled separation, or cascading failures. So those are the three evils they call. These are the, like the lawyers, right? The Congress, the lawyers' definition. So engineers, like myself, we took this legal definition and put it into more numerical or engineering concept. The frequency, voltage, and we also wanted to restore, right? Once we have blackout, how do we restore? And how do we measure do we have enough generation to serve? And here's the one that I put it into the red color for the low probability disturbance, like the one in Texas, like the one in New York area. Those that we don't see those events every year. We see it probably once every 5 years, once every 10 years, or more often. These are the events. It doesn't say that we cannot have a rolling blackout. It just says that as long as we manage these events, we'll be okay. So again, to answer the questions I had earlier, was grid reliable during the blackout or during the Texas rolling blackout events? The answer would be yes, because according to the legal definition, and Texas did not have, let's look at this legal definition again, did not have instability, uncontrolled separation, or cascading failure. They had rolling blackouts. Rolling blackouts still says the system is reliable. So that's what the definition we have here. Like I said, it's a legal, it's a lawyer, it's a government's definition. Everybody follows that definition. And so they design their grid, so they add transmission lines or generations and do a lot of things and try to keep, have the lights on, and meanwhile try to avoid instability, uncontrolled separation, cascading outage. So that's the definition. Once we know that, it will be much easier to get into vital signs. So now we know the reliability. So what are the vital signs? So I worked at NERC, which is a industry standard reliability standards organization. So we came up with 13 reliability vital signs, like your pulse rate, blood pressure, BMI, like cholesterol level, all that. So here's 13 for the industry. So we know when we have the change with the renewables, with the storms, everything that come into the grid, is system reliable or so? Or then the question, how is the health of the grid? We use these 13 the vital signs to measure. Okay, the first one is reserve margin. Okay, that's the important one. That means that do we have enough generation to serve my load? And second one is also important, is that do I have any blackouts? I mean, do I have instability? Those three evils. And then this frequency response is that if I have a lot of inverters, right, a lot of static inverters like DRs or the storage, all those come into my system, wind, and how do I have enough inertia to respond to my generation loss? So that's how's my can my frequency still at 50 hertz or 60 hertz after I have a sudden loss of big generators. And the others, those are the measures, those are not important as the first few. And this one, M9, is very important as well, correct protection system operation. And 11 is a good too, like Texas, they use this one to decide when to shed the firm load. So these are the ones that, and these are the more on the transmission availability side. And then you can find this at the NERC.com. I have a link later on. So you can see how we use that, how we collect the data. So this is the first one, reserve margin. By the way, if you have any questions, please put into chat, or you can just unmute yourself and ask questions. Now, I like to have a conversational talk, so that just not me and talk all the time. So here you can see that each area, the planning area, they all forecast do they have enough generation. So here's 2019 summer, the ERCOT, which is Texas. They said, oh, I don't have enough. And this is the kind of their, we call the reference line. So I like to get this point, this black bar, but I don't have enough. And then they forecast they will be short. So they said, I will have plan to shed the demand response, to shed the load. So if I'm getting tight, I don't have enough generation to serve my load, I have a program that I can ask my load to come offline. And that's exactly what they did in 2019. Okay, so you can tell most of the regions, they are comfortably, they have enough generator capacity to meet their load. But Texas, they said we didn't have enough, but they didn't manage with their demand response program. So this is the one I said these are the outage transmission, because of transmission outage and caused the firm load loss. Like I said, in 2003, the huge blackout, we lost about 80,000. And here in 2015, you can tell from after the mandatory standards and Congress intervention, so from 2015 to 2019, and we the outages, we still have some outages, and you can tell here's the average is about 7 no, actually the average, yeah, demand. Okay, the average is I would say probably around 10 each year. And what I want you to notice is that this red line, it just says we only have about 200 megawatts for each event. So which is very low. You probably don't notice it. It will be a community of probably several local communities. It will not get on the TV or get on the news. So this is a great reliability improvement story. Even though we had the hurricane caused the electricity loss, but those are the ones that we cannot fix, right? Those are the ones that we cannot prevent. But these are the ones, if we avoid, if we can reduce human error, we reduce equipment failure. Those are the things human can do, and try to eliminate the root causes. We can reduce further. So this is a great story that reliability has been improving. This is a frequency response. Like I said, can we tell if the whole system's inertia is going down or keep constant or going up? This one is the big transfer capability. So if I have a lot of big generator from west, and they all going to New York City, right? So what do I have stability limit or any other transfer limit, thermal limit? This one measures that. You can tell most of the time we have this blue. Yes, we went over the limit, but it's less than between 10 and 20 minutes. What we try to avoid is more than 30 minutes to reduce the risk. And this is one I like to spend a few minutes on this one. The protection system operation here in North America, you can tell the average is about 8%. What does that mean? Meaning that that if we have 100 protection or relay operations, and 8 of them were wrong. Either they trip the line, they're not supposed to trip, or they're supposed to close the line and didn't close. So those are the numbers in North America, and we find out that during every events, like the events we see here, all the low loss events, most of the time we'll find one or two relay misoperations. So we need to reduce the number of misoperations. So the scale of these, the blackout, all these load shed events will be reduced. Instead of 200 megawatts, and we could go to 100 megawatts load shed if we can eliminate the misoperation. So this is the key. So if you're studying the power system, and I would encourage you to take a lot of classes in this area, because this is where we need a lot of help. So we actually look into the data and to see what caused those misoperations. You can tell more than 30%, 1/3 of it, is caused by incorrect settings and logic errors. That means the engineers, the relay engineers, they did not have the right settings, logic, or design when they start the relay. And there are some other, like the technicians in the field, those are less than 10%. These are right here. There's hardware failures, communication, and relay failure. Those are hardware failures, but those are not, well, here we have about 20%. So that's another area we need to look into. The mainly, like I said, more than 30% was caused by incorrect setting, logic designer. And we need lots of relay engineers in North America, so we can reduce these errors, and so we can reduce the total number of misoperations. Another indicator that we have is overall. It's like the hurricane, is it level 1, level 2, level 3? So we have that as well. So we have lots of disturbance in the grid. Then there's like small risk ones we call, for instance, 1 unit trip or 1 line trip. Those would be under the reporting threshold. And we also have the higher, like Texas winter storm event or the hurricane event. Those are the ones, low probability events, they're here. And these are the ones at the low risk level. We accept their risk, right? Because we know the lights will be on. So the ones we try to learn and reduce is this green area, is the one that I showed you, the 200 megawatts a load shed. We still have 10 events each year in North America. So if we can keep working on these areas, then we can reduce the impact of these, the red, the severe events. That's the idea. So we created this indicator. It's called Severity Risk Index, SRI. It's a stress indicator, and to see how many lines and how many outages that we could take without losing the system. So here's now we plug in through the real data. So if you look at 2010 to 2015, all the ones you can look at the top 10 events here. All these caused by the weather. And here's the table shows the SRI numbers. You can tell in 2015 top 10 SRI events. They all, here's the event type, either storm, severe weather, showers, and summer weather. So these are all caused by the weather. None of them, all the severe events, none of them are caused by the human errors or the ones that we can avoid. And again, Blake said, we also plug into the 2003, the huge blackout I said earlier. The highest SRI is 80. This has been the highest we recorded. From these 8 years, 2008 to 2015, and you can tell the top one was the blackout event in San Diego. And the rest of all these events are weather related as well. So this indicator gave us a way to the comparison, which one is the worst. So how do we improve the reliability, and how do we reduce the impact? So that this gave us a lot of information. Like I said, you can find the definition and the trends and data analysis at this link. I was at the NERC for about 6 years, and we built the team and came up with those 13. And every year, like I said early in the at the beginning, is we have the annual checkup, right? We look at those 13 vital signs and look at the grid, and based on the data. Data is our kind of our blood draw. You get the data and you look at the trends and compare, look at your baseline. We built our baseline in 2012 and 2013. Then you can see if we're getting better or worse. So, and if we see there's improvement area like a protection misoperation, then we will have a standards and try to improve the standards and reduce those misoperations. So it's kind of the closed feedback loop. The other things, like I said, those high impact, low probability events, those are the ones that keep us awake. So we have to find a way to work together, and because no company, and normally those events are so big, and we have to work together to restore the system and to help the customers and get back on. Again, I want to summarize the history, if you want to see why we are, and to explain what we've seen today. And we have to understand the history, because it's more than 130-year history. And we've started with the science and technology, right? The Thomas Edison. Then we had a business strategy like Samuel Insull, the flat rate. Then we have Lauren courts. Like I said, 2003 we had a blackout, so the government came up with the law, and there's a regulatory policy and politics and culture. All that are part of the great history and great culture. So it's not that easy to change to accommodate a lot of new things quickly. So we have to work together to make the change, to make the change faster. So again, it takes all of us. If you're a student still, and we need you. And if you're a professor, we need you as well. And manufacturers, yes. Generators, of course, we need the resources. And T&D company, the grid company, yes, they are our infrastructure. They are our kind of lifeline. And we need also, we have a market. If we have a market, we need operators. Standards, of course, and government regulation, yes, that would help. And also you can see the demand. You can help too. If you're the user, if you have the demand response program, yes, you can actively and help the grid, help the reliability. And of course, you can always do the energy efficiency, right? And to lower your temperature in the summertime, and also turn the lights on if you're not going to use it. Associations, the PES is one of associations. There are many other associations. We try to leverage our collective wisdom and try to face a challenge and create opportunity for everyone. Of course, if you're entrepreneur, and yeah, go with a startup and use the new technology, your innovation to help. So I want to give you example how demand response could help the reliability. So here is in 2011, the regulators here issued orders that demand response, the load can be paid the same as a generator. But the generator association, they didn't like that. So 3 years after, they actually, they went to the court, and 3 years after that, the court issued the judgment says, yeah, I agree with you. Generator should not be paid as, the load should not be paid as a generator, because generator can do more. Like the reliability survey, they provide regulation, voltage, control, and all that. But the demand response cannot do it. So, but then the Obama administration took that to the U.S. Supreme Court, says we disagree. with the lower court decision. Here's why. The loads can help the reliability, especially during the peak time. This is where the electricity price are the highest. And the US Supreme Court, all the judges agree with Obama administration. So they ruled in favor of demand response 2 years after. So the example, I just want to let you know, yes, there's a politics and there's a the law and courts. They all part of the reliability equation. So because of this ruling in 2016, now here in the US, all the load response program that bid into the market are paid as the same as generators. So that encourages the load to participate. So not just generator, not just transmission or distribution company, generator can play, the load can play a big role in reliability. So here's the one version of the future grid, right? Now we want to have not just reliability, not just low cost, and not just safety. We want resiliency. We want flexibility, right? All these things. So I think so you can tell these are the leading trends. So if you're you wanted to study in this area, and if you have interest in any of these areas, the demands and the fuel, and or T&D, and we have lots of like data analytics, AI, machine learning in T&D areas. Also, you will see more customer choice. Like if you have a DER, and you can decide what to do, and you have an EV, you can decide. All these are booming. So if you like I said, if you want to study and pick any research topic or any classes, and you will have a bright future. Right, there are tons of job opportunities for all these areas, and particularly the government, the FERC, our regulator here, issued order 841 energy storage, encourage energy storage to compete with the traditional generator. And we also issued the order 2222 and encourage all the distributed energy resource to compete with the traditional generators. So this one was ordered, this one was issued, the energy storage one was issued in 2018. The DER one was issued last year, September last year. So the goal is you can tell, is to cut the cost, so we can get all these new things, the big data, AIs and DERs get into the system, including energy storage, into the system quickly. Who's going to benefit? Every one of us, right? The consumers. Are we ready to do it? I think we are, and PES has more than 40,000 members in 150 countries, including your part of the world. And we have 10 regions, you're in region 8. We have, this is probably old, we have more than 400 student chapters, exact like one of your chapters. And we have more than 250 professional chapters, the regular members. And you can tell because the industry has been transitioning to the new, kind of a new place. And we had a tremendous growth for the last 15 years. Our membership has doubled. However, we still have the same challenge. If you look at, this is the Chicago winter, December winter load curve, right? During the winter cold evening hours, the load was very high. So our challenge has always been, how do I serve the load and also lower the cost? So well, the traditional ways is build more power plants, right? And so we can, the peak ones, whenever we need it, we just start right away. And once the peak hours are over, then we shut those generators down. So it costs a lot. And here's a believe it or not, and here's the 1898, and we had a world's largest storage battery here in Chicago to try to serve these peak hours. So they had the same intent as we are having today, is to, how do I save? How do I have the energy storage? So I charge during the evening when the price is low, and I discharge during these peak hours. And here's the current load curve with lots of solar, wind, and you can tell, and especially when sun comes out, wind is here, the load actually drops, right? And here's the kind of the period without sun, without wind. And here's the when sun goes down and wind is less, then you still have this peak load. So can we use the new technology on storage and to cover this load period so we don't have to build those big power plants? They pollute the environment and they're also very expensive. So this is the same challenge we had for last 100 years, and we still have not resolved, have a good solution yet. So that's a challenge. Another one, so if you're a PES member, you can get all these resources free at the PES Resource Center. I just want to show you the top downloads last year. So you can tell the COVID was very a kind of focused area, and there's a microgrid, there's a the inverter dynamic behavior, and also the energy storage. So you can tell if you're doing any research or write a technical paper and try to set up the lab. So these are the ones, these are the worldwide numbers. You can tell that we have all these trends here. So if you want to decide which area do you want to look into, these are the area could give you some hint. Like I said, opportunity looks like work, but it's I mean, especially that the young generations will take another look at different effects and help us to solve the problem. The PES membership is very diverse. We have PVs and renewable energy, and we also have a traditional generator and TNT. Young professional for all the members that after they graduate from school with a bachelor degree up to 35 years old, we call them young professionals, and we have more than 6,000 young professionals. So being part of the PS, and you can connect with young professionals and help each other. We also have a Women in Power. I think Mercy, and Mercy, I think, is the vice chair of our Women in Power. And there are many women, or even gentlemen, they come in to join this group. I have been a part of this group for many years and help us to advance our career, learn from each other, and help each other and support each other. So yeah, please join the Women in Power. It could be anyone. It doesn't have to be ladies or the women. It could be any gender. That's all I have. So I just wanted to thank you again. If you have any questions, please email me or talk to Mercy or Chris, and they will be able to find me. Thank you. Back to you, Chris.
Hello. Hello.
Yes, I can hear you. Any questions?
Yeah, thank you very much for that. A wonderful presentation and well organized. So my question is,
I think I lost you. You muted, looks like.
okay, sorry for that. So my question is, how is the smart grid being improved to improve on the grid reliability?
How do you, let me repeat, how do I improve the grid reliability?
So I'm asking, how is the smart grid being prepared to improve on the grid reliability? Because there is a talks on the technology of smart grid. So I was wondering, how is the smart grid being prepared to handle all these vulnerabilities that are being experienced in the normal grid?
Yes, that's a great question. Let's see if I can go back to my yes, it will, because if you think the smart grid, it's smart, right? And what do you mean? So what do we mean by smart? So let me see if I can get this back. So here, these are the things we're being working on. So the smart grid, this would be look like a smart grid, right? With everything that we can dream of. We can have the smart building, smart city, smart village, and with all the EVs and biomass and everything you can dream of. That's the kind of ultimate version of smart grid. But to kind of break down a little bit, these are the 4 areas will make grid more smarter and more reliable. For instance, the TND, I said, if we can deploy the big data, AI, intelligence, and we would know, right? And now we also have a digital twin, and we would have a kind of ears and eyes to the grid, so we would know exactly what's going on. And instead of just the lines, right? In the past, it's relays and controls and lines without knowing do I need to fix and how do I avoid the equipment failures. If you look at these charts, look at what I have here, this one. So these are we still have about like 10 events each year. So how do we reduce that? And the smart grid would do. If we reduce to 0, and that improves that means we don't have any load shed at all, and that the smart grid will tell us when to fix the equipment before it fails. These events are caused by failed equipment or human errors or the other outage. So with a smart grid, and we would know, okay, this transformer is going to fail before it comes out on its own. I can tell. I have sensors. I have AIs could tell me. I can pinpoint where the fault point might be, so I can fix it before the disaster happens. So yeah, to answer your question, definitely all those things would help. All those technologies around the smart grid, all these like 4 areas will make the reliability much better.
Okay, thank you. That is great.
Hello. Thanks. I'm Ben from IEEE Kenya Moi University. So my question is there any power mechanism that are set aside to ensure there's an official technology documentation for the smart grid system?
Okay, let me see if I understand. You're saying, do we have any formal definition on the smart grid?
I said, is there any like robust mechanisms put in place to ensure there is an official technology documentation for the smart grid? Because most people hear about it and simple implementations, but they don't know, like, if I want to implement one on a smaller scale, what's the starting point? What's the starting procedure? What are the best practices? Like, it's something that is official that can be followed to ensure like a better implementation of this technology. That's what I meant.
Yes, that's a good question. Yes, so the IEEE has the PES, and with other societies at IEEE, we have IEEE Smart Grid Initiative or Smart Grid Resource Center. There you'll find the smart grid definition and best practices, the standards, especially for the communication. How do we integrate with the data stream? How do we integrate with the renewables? All that is on the Smart Grid Resource Center. So if you Google it, IEEE Smart Grid Resource Center, you'll find all the definitions and the best practices. They have free webinars, and they have many documentations on the standards and how people use the smart grid technology. Yes. Does that answer your question?
Yeah, it's fine, and thanks for the great session. I really enjoyed it.
Yeah. So it's directly called Smart Grid Resource Center. If you Google that, you'll find tons of information.
Hello, Jessica. This is Paul Kanja, IEEE Kenyatta University Student Branch. So first of all, thank you so much for this insightful presentation. And maybe just to bring to the board in terms of the Kenyan grid situation. So we have the National Control Center that tries to man all the electrical controlling of the state. However, some of the challenges that they recently experienced includes the integration of the variable renewable energies, and this comes along with the installation of the 300 megawatt wind power plant, and also the 50 megawatt Garissa power plant. So some of the issues comes with the high ramp rates that are being experienced from these kind of systems. However, this is an area that maybe researches can be done on the right way of integrating the variable renewable energy to the grid, owing to the fact that the Kenyan grid is roughly 92% renewable energy. So then you find this kind of unreliabilities comes along. And we believe, of course, issues like the smart grid also is not just being smart. There is issues of data protections. And I know this has also been breached in some areas within the United States where we have this kind of pilot schemes of smart grid systems. So then, there's quite a lot that is supposed to be done. But within the Kenyan scenario, so maybe a lot could be done in terms of the research work on the variable integration or the integration of the variable renewable energies to the grid, and how to maintain the ramp rates and other variables that bring along the unreliability of the grid. Thank you so much.
Yeah, good, excellent. Thank you for giving me an overview of your problems or issues, the challenges. So do you have a market, like wholesale market, like system operator? They can buy the quick ramp regulation?
So in Kenya, we do not have that bundled category. We have KenGen as the generator. Then we have the Ketraco, who operates as the transmitter. Then we have the Kenya Power, who are the distributors. And then we now have the regulator, who are the Energy and Petroleum Regulatory Authority. And all this falls under the Ministry of Energy. So it's not really bundled together. And I think that's now where we have issues, because all this cost and the controlling aspect. The NCC is under the Kenya Power and also is manned through the Ministry of Energy. So, of course, we have these kind of issues that comes with unbundled systems, for example, here in Kenya.
Yeah, okay. Yeah, so we had similar issues at early stage. So eventually we came up with the wholesale markets. So what the system operator does, they just buy more quick ramp reserves. So when they know that, yeah, okay, 7 a.m. or 8 a.m. when sun comes up, or wind comes in, then they know they need a quick ramp, either in and out. So they will buy more reserves, the quick reserves or regulations for those 15 minutes or for those intervals. And those could be very expensive, especially they need a lot. Like Texas, it's a smaller grid, so they will buy more compared with the Eastern interconnection, which is huge. So they can buy less. That's how they. So it's not free. By integrating the renewables, the wind, it's not free, because we have to buy more regulations to accommodate for them to come in. And that's how we use a market to kind of balance it out. Yeah, another way that PJM has been doing here, one of the system operators, they get the energy storage. So those are quick charging, discharging. So we have a lot of energy storage, the batteries in our regulation market. So they come in, it's a new technology, you can do lots of research, and also it helps reliability. So those are the, so to me is that if we can, like you said, if we unbundle, but we have a fair competition, we have a market, and the storage, or the even fuel cell. We had a couple of fuel cell technology to look into, can they get into the regulation, and this was about 10 years ago. So now the energy storage seems like a trend. Everybody's trying to get into it, and so they can provide regulation, not just the energy from the storage. They can do a lot of reliability help as well. Yeah, and that goes back to your the cyber attack and cybersecurity. Yes, that's the kind of the challenge of pain for all of us. Once we want to grow, want to connect, and the cybersecurity is always a threat. So what we did, especially the organization, the NERC, I said NERC. If you Google NERC, they have about a dozen of reliability, cybersecurity, and physical security standards, and that's what industry here uses to prevent the cyber attack or lower the risk of cybersecurity and physical security. So if you want to know how we did it, you can go to the NERC website and find their standards. And like I said, everybody, all the utility companies, they have to follow. Those are the government regulations. So we follow them. And it seems working, and they change very fast. Now I think it's up to version 7. So every couple of years they have a new version comes out, because the tech industry and moves very fast. So that's how we keep up with it.
Thank you so much.
Sure. Yeah, it's kind of the growing, it's a learning curve, and once you see the issues, then so and all these issues you mentioned, all the opportunities you mentioned, we've seen it, and so please join PES, the conference or events or webinars, because we have lots of, it's a worldwide association, so we have lots of folks that they've been there, done that, and you can tell probably some of the issue you face, we've never had it before, and you can tell us how you resolve it. We learn from you, and for some of the issues that the other parts of the world, they already have it, and you can kind of have change information from them and to see how they resolve it. And they're very similar issues. I know the grid, the connection, maybe the dynamics are a little different, right? If you run, but some of the fundamental issues, like you said, right? Once we have more variable, the wind and solar into our system, yeah, we have to increase our reserve, and yeah, we've done that, and it's going to increase the cost, of course, right? And the market would be the best way to resolve, is because you have a fair competition, you can mutualize the technology. It's not just the traditional generator to increase the regulation. You can have all kinds of, like I said, we have even the inverters nowadays that they said we can provide all these regulations, because they can do it very fast. So that remains to be seen. We have not seen it, but energy storage, certainly we have seen it. They're in the market right now. Any other questions? Okay, if not, back to you, Chris.
Okay, thank you very much, Jessica. I think this is the best way to spend an afternoon here, because we have really learned, and that was very informative session. Once again, we are also very excited to host the President Power and Energy Society. That was an honor having you give us a talk. I also would like to thank you who spent their time to join the webinar. I hope you learned, and also we recorded the webinar. We'll be sharing later after this talk. Maybe the webinar was in partnership with YP Kenya and IEEE Moi University Student Branch. maybe I can invite any YPD representative to say a word before we end the meeting.
Sure.
I see the YP chair. Maybe Kidenji, if you can be able to.
Yes, thank you. I hope you can hear me.
Yes, I can.
Oh, perfect. So I've joined in late, but I think I've made the discussion at the point where Jessica was trying to show how important the smart grids are, and also the questions that you guys are asking. I think they really tell how the discussion has been. So mine is just to say thank you very much, Jessica, for providing this talk to the section, and also by sharing more insights that really we need, especially us here in an economy that is really growing very fast. To Chris, Ben, and Beryl, the rest of the Moi University team, keep on doing this, because I think we really need to keep on leveraging on the expertise and the knowledge that is there outside there. And I can also see we have Engineer Paul Kanja here. I think it's also nice to have expertise kind of guys coming in and trying to listen in. So this is a great job, Chris. Keep on doing this, and I think we have a future that is really bright. Thank you very much all for attending, and thank you very much, Jessica, for sharing this with us. Be blessed.
Thank you, Muriungi, for that. And thank you once again, Jessica. I hope we'll stay in touch for future so that we can have more of this engagement in the future. And thank you very much, Asanteni Sana, for who joined in. We also appreciate. It was a wonderful afternoon. That is the end. And if you have any question, maybe you can forward to me. I can forward to Jessica, and she can respond anytime. Anytime. So thank you very much. The talk was supposed to be 1 hour 15 minutes, and we have kept time. I think it's very exciting. Thank you very much. Have a good afternoon, and have a good morning to you, Jessica. Bye.
Bye.
Bye-bye.